Hello, everyone, and welcome to Calculus 2. I am your host, Sam Smith, and the goal for this video is a broad strokes overview of the ideas of Calculus 2, as well as an overview of some of the math classes that you would have taken before Calculus 2 to reach this point, as well as a very quick overview of the math classes that would come after Calculus 2, especially if you're planning to take a STEM degree, for example, a degree in mathematics, a degree in physics, or a degree in engineering. You start off in arithmetic, and arithmetic is all about how to manipulate numbers. And arithmetic is where you learn how to add, where you learn how to subtract, where you learn how to multiply and divide numbers, whether they be whole positive numbers, whole negative numbers, fractions, decimals, percents. Arithmetic is all about manipulating numbers. Now, when you get into algebra, you get introduced to the concept of a variable, representing a number that can change or a number that is unknown. And this is where you learn how to do things like manipulate expressions. This is where you learn how to do things like solve basic equations. And this is where you learn how to do things like graphing, how to create graphs, how to read graphs, how to interpret them, make conclusions from them. Now, as you get into pre-calculus, you learn about the concept of a function. And this is where you learn the important, what we call toolkit functions. The toolkit functions are the basic mathematical building blocks that are used to express most of what happens in the world, things that change over time, quantities that affect one another. This is where you learn about things like linear functions, like the absolute value function, things like quadratic functions, things, for example, like the exponential function, super important for representing population growth, temperature change, most of stuff to do with money, finances, loans and savings, that kind of thing. Then here's the one that everybody really seems to hate, logarithmic functions. And then as you get into pre-calculus 2, this is typically where you start to learn about the trigonometric functions, things like sine, cosine, tangent, and their inverses, inverse sine, inverse tangent, that kind of thing. Now in calculus 1, you're starting to learn about the derivative. Calculus 1 is all about the derivative. And the derivative of a function has lots and lots of different applications. The derivative of a function tells you how fast the function is changing. It tells you its instantaneous rate of change. So it can be used to do things like take a position function and figure out how fast the object is moving, the velocity function. And one application of the derivative is to rates of change. Another really important application of the derivative is to what we call optimization. You may remember in Calculus 1 that the derivative of a function told you the slope of what we call the function's tangent line. And if the tangent line had a slope of 0, if the tangent line had a slope of 0, then that told you that the tangent line was horizontal because a slope of 0 indicates a horizontal line. And when the tangent line had a slope of 0 and the tangent line was horizontal, that was a sign that you were probably dealing with the lowest point on a graph or the highest point on a graph. Maximum or a minimum is what we said using the mathematical terminology. And so derivatives telling you the slope of a tangent line, telling you where the tangent line becomes 0, give you a way to figure out where the maximum or minimum of a function is, and that is used in problems of optimization. Now these are the things that the derivative is used for. a lot of the time that you spent in Calculus 1 would have been how do you calculate the derivative for various functions? And that's going to be really, really important information for you to know and remember as we transition into Calculus 2. Because a lot of the things that we will be doing in Calculus 2 are going to be a lot easier if you have memorized your derivative rules. Now that we have finished Calculus 1, we have now arrived upon Calculus 2. You are here in Calculus 2. So let's take a quick detour and talk in some detail about what Calculus 2 is all about, and then we'll circle back and I'll tell you a little bit about what is happening in these classes which are coming after Calculus 2. So Calculus 2, Calculus 1 was all about this thing called a derivative. What's Calculus 2 all about? Calculus 2 is all about a new mathematical object that you'll be introduced to, that you'll learn how to calculate, something called an integral. What is an integral? Well, in basic terms, an integral is a sum. An integral is a quantity that is obtained by adding together a bunch of numbers. And to explain what I mean, I'm going to walk you through a couple of scenarios. I'm going to walk you through a couple of really the most quintessential applications of the integral, some of the most common things that an integral is used to do. To that end, let's go ahead and dive into this scenario of distance traveled by a moving object. And we'll start off with a really, really simple, basic scenario that you might have encountered as you completed, for example, arithmetic or algebra up here in your previous math classes. So scenario number 1, you got a car and it's driving, and let's suppose that the car is driving at a constant speed. It is staying at a speed of 30 miles per hour, and it remains at that speed for half an hour. If you want to know how far the car traveled during this half-hour time interval, what would you do? Take a minute, think about that. Now, you may be familiar with the equation known in algebra as dirt. D equals RT, D-E-R-T, the dirt equation. This equation captures what most of us, I think, understand intuitively. That if you want to know how far an object has traveled, you take the rate of travel, the speed at which the object is traveling, and then multiply it by the length of time that it has traveled at that speed. Distance is equal to rate times time, dirt for short. So if someone asks me, how far has this car traveled? During this time interval, all I have to do is take this speed, this rate of 30 miles per hour, and multiply it by the amount of time that it traveled at that speed. So 30 times 0.5, giving me a result of 15 miles. Now, that was an easy calculation, but it's not really realistic. Most of the time, if you're dealing with a car that's traveling for any length of time, the speed isn't actually constant. The car may speed up or slow down. It may come to a complete stop. So if you have a car, for example, which is driving at a non-constant speed, in that situation, how would you handle the distance traveled? So to explore that situation, that slightly more realistic situation, let's have a look here at scenario number 2. We have a car, but it's no longer driving at a constant speed. Instead, we have a table, the number on the speedometer as recorded at a couple of different times. Let's try and use this information to get a reasonable estimate for how far the car has traveled. So this table says that when no time has passed, when the car is initially setting off on its journey, it initially has a speed of 0 miles per hour. Then you turn the car on, you put your foot on the gas pedal, you accelerate, and at time 1/2 hour, we record a speed on the speedometer of 5 miles per hour. When 1 hour is passed, the driver looks down at their speedometer and records a speed of 28 miles per hour. After 90 minutes, it's 35 miles per hour. And at 2 hours' time, we look down at the speedometer and we record that we are driving 17 miles per hour at that time. So let's try and estimate how far the car traveled during this time. Now, this problem is pretty vague. There are a lot of different ways to think about and approach this problem. And this is something that you are going to encounter a couple different times during this class. A problem that's somewhat vague, that doesn't necessarily have one correct answer, a question that requires you to make some decisions on your own about how you want to approach the problem. So let's go ahead and let me demonstrate for you how I might approach a problem like this one. So one possible approach to a problem like this one would be for me to say, okay, I do know that if an object travels at a constant speed, then you can find the distance traveled by taking that constant speed and multiplying it by the length of time that the object was moving at that speed. So what I'm going to do is I'm going to assume slash pretend that the object was moving at a constant speed essentially at all the different time intervals between what is explicitly recorded to me in this table. Okay? So, for example, I might assume that, or pretend that, between time 0 and time 0.5, that the object was traveling, the car was traveling at a constant speed of 5. I'm going to assume slash pretend that the object speed was a constant 5 miles per hour between time t equals 0 and time t equals 0.5. I'm going to do that because that assumption gives me enough information to actually do a calculation. If I make this assumption that the car's speed was constant between these two times, then with this assumption, I can calculate the distance traveled between these two times. I can calculate that the distance traveled between these two times was the speed that I'm assuming was constant times the length of time that the object was assumed to hold the speed. Using that dirt equation, d equals rate times time, I'm going to assume that the object traveled, the car traveled about 2.5 miles in this first time interval. Now, is this assumption correct? Is this assumption even reasonable? That's debatable, right? For sure, the object speed was not constant between 0 and 0.5. The car had to accelerate from a speed of nothing to a speed of 5 during this time. But making that assumption is necessary to be able to do a calculation. And after all, the question just asks me for an estimate. So I'm going to do what I have to do in order to make the problem straightforward enough for me to do a calculation. I'm going to make a similar assumption about each of these other time intervals as well. I'm going to, for example, just pretend that the car's speed between 0.5 hours and 1 hour was a constant 28 miles per hour. With this pretense, with this assumption, I now have enough information that I can do a calculation. Because if I assume slash pretend that the car's speed was constant between these two times, then I have enough information to estimate the distance traveled. If I make this assumption, once again I can use the dirt equation to say that the distance traveled between these times was given by the speed between those times, 28 miles per hour, multiplied by the amount of time that passed. And the amount of time that has passed between 0.5 hours and 1 hour is a time interval of half an hour. A half an hour has passed between those two times. So 28 miles per hour held constant for half an hour would give us a distance traveled of 14 miles. And I could keep making this assumption. I could keep making similar assumptions for all of these time intervals. I could, for example, assume that between time 1 and time 1.5, the speed of the car was constant at 35. I could assume that between time 1.5 and 2, the speed of the car was constant at 17. Now, if I make those assumptions, then the distance traveled by the car between these two time intervals, between 1 hour and 1.5 hours at a constant speed of 35 miles per hour, for that half hour time interval, car would have traveled 17 and a half miles. If it then the next and the last half hour, if I assume a constant speed of 17, then we could do 17 times the half hour amount of time that's passed, and that would be 8.5 miles. And now that we have found the distance traveled, or I should say, now that we have estimated the distance traveled by the car between each of these time checkpoints, then how would I find the total distance traveled, do you think? We could find the total distance traveled just by adding these four calculated values together. 2.5 plus what we calculated earlier to be 14, what we calculated earlier to be 17.5, what we calculated earlier to be 8.5. The sum of these values would be an estimate for the total distance traveled. Now, most of you probably intuitively know that this estimate for the total distance traveled by the car is probably going to be pretty bad, probably going to be pretty inaccurate, right? Because this calculation was based upon a pretense, was based upon an assumption that doesn't seem particularly valid, right? How can we assume that the object's speed, the car's speed, between zero point 0.5 and 1 was constant at 28? That doesn't feel right, right? So maybe some of you would be inclined to try and take the average, like maybe the car's speed was actually closer to the average of 5 and 28 between these two times. That is absolutely a valid approach to the problem, to average the initial and final speed and use that to do the calculations. And there are many, many other ways to approach a problem like this to get perfectly reasonable estimates. Generally speaking, the estimate becomes more reasonable the more work and thought you're willing to put in. There's another way to get this estimate of total distance traveled to be better. You know, this driver has only recorded their speed in these half-hour intervals, right? They recorded the speed at time 0. They recorded it after a half hour, after 1 hour, after 1.5 hours, and finally at 2 hours. But we might be able to get more accurate information about the car, what the car is doing, if we simply recorded its speed more often. For example, in this scenario, instead of the driver recording the car's speed every half hour, this driver is recording the car's speed every 6 minutes. Now, you could use the same idea, the same kind of assumptions that we used in scenario 2. You could say, I'm going to pretend, I'm going to assume that the car's speed in these first 6 minutes was constant at 1 mile per hour, I'm going to assume that the car's speed between 6 and 12 minutes was constant at 2 miles per hour. I'm going to assume that the car's speed between 12 minutes and 18 minutes was constant at 3.1 miles per hour. And if you make assumptions like that, assuming that the car's speed is constant for certain periods of time, then you can do the same kind of idea that we did in the previous scenario. Multiply the speed of the car by the amount of time that the car moved at that speed using the dirt equation to get the distance traveled by the car during that time interval, during that period of time. And then you can add together all those little bits of distance traveled, and the total, the sum of those distances, would be an estimate for the total distance traveled by the car. So, thought exercise compared to scenario 2, where the amount of time between your data is really big, which is going to give you the more accurate estimate? Having sparse data with big gaps between it, or having more fine data with less distance between your times, with less distance between your pieces of data that you've recorded. Intuitively, you probably can guess that the more data that you have and the smaller the amount of time between recordings, the more accurate your estimate is going to be. If the time interval between recordings is small, then the car simply doesn't have as much time to do weird stuff and to deviate from the values that have been recorded in the table. So you're probably getting a much better estimate as you have more data and your intervals between the times are small. Now, if you take that idea to its natural extreme, then you could say to yourself, if you wanted your estimate of the distance traveled to be very, very, very accurate, then what you would need to do is collect a huge amount of data. Maybe record the speed of the car every second. Maybe record the speed of the car every millisecond. The shorter the distance between recordings, the more accurate your estimate of total distance traveled is going to be. This idea of taking a sum of recorded data and taking it to its natural extreme of recording a ton of data with very few gaps between the information that you've recorded is the idea behind an integral. An integral is a sum. An integral is a sum that has become extremely accurate as the intervals between the recorded data gets very, very small. A sum that has become very accurate by making the intervals between the recordings very small. To give you an example of how we would use this word in practice, in the previous scenario, we would say that the distance traveled by the car is an integral of the car's speed. In particular, we would say it's an integral with respect to time. Because we got distance traveled by adding up the car's speed multiplied by the length of time it traveled at that speed. And as the amount of time between the recordings gets smaller and smaller, then our estimate of the distance traveled by the car gets more and more accurate. So we would say that the distance traveled by the car is an integral, a sum of speed with respect to time. More on that as the class proceeds. That's the basic idea of the integral in Calculus 2. The integral is a sum. The integral is super useful as a tool in physics. Fun history fact, historically, the integral was actually the first bit of calculus that was developed by Isaac Newton. Actually, the way that we learn calculus in school is almost completely opposite of the way that it was developed historically by Isaac Newton. In school, we learn limits first, and then we learn the derivative, and then we learn the integral. But historically, actually, the integral was developed first, and after that, derivatives were invented, and after that, limits were invented. The integral is incredibly useful in physics, not only for distance calculations, but let me give you another quick example of one thing that the integral can be used to calculate. Let me give you an example of mass. So in this scenario, introductory scenario, basic stuff that you can do using just arithmetic. Suppose that you had a rod, for example, a metal rod. It was 10 centimeters long. And the density of the rod was constant. The rod is made of the same material, same thickness throughout the entire thing, and it has a linear density of 5 grams of mass accumulated with every centimeter of length, 5 grams per centimeter. Based on this information, how would you find the mass of the rod in total? Well, if density is saying that there are 5 grams of mass in every centimeter of length, and the rod is 10 centimeters long, then we could estimate the total mass by just taking that density of 5 grams per centimeter and multiplying it by the total of 10 centimeters. Just density times length, giving you a total of 50 grams of mass for this rod. But once again, just like the example with the car, it may or may not be true that you're working with a rod whose density is actually constant like this. Maybe that you have a rod whose thickness varies, or which is made of different materials, maybe alloyed metals throughout, and the density of the rod is different at different points on the rod. And the density of the rod is recorded at various positions along the rod. So for example, if the rod looks like this, what a terrible drawing. If the rod looks like this, then they record the density of the rod 0 centimeters from the left. The density is recorded as 2 grams per centimeter. Then, 2 centimeters from the left side, the density is recorded as 5. Then 4 centimeters from the left side, the density is measured and recorded as 7, and so on and so forth. If you had a rod that looked like this and behaved like this, then the question is, how would you estimate, how would you get a decent estimate of the total mass of the rod in this case? Well, once again, you can use the same idea that we used with the car in the distance traveled example. In this situation, you can make some assumptions. You have to make some assumptions in order to make this estimate possible. For example, you can assume that this first chunk of the rod has a constant density. You could assume, for example, that the density of the rod between the left end point and the right end point is somewhere between 2 and 5. Like maybe you decide to estimate that it's about 3.5 grams per centimeter. Maybe you decide to average the density on the left and the density on the right. And once again, I emphasize that this is an assumption. This is a pretense. The rod definitely explicitly does not have constant density on this interval because the density on the left side and the density on the right side aren't the same. But we make this assumption to make it possible to calculate the mass of this little chunk of rod. I would say the mass of this little chunk of rod is going to be approximately the density of that little chunk, which I have assumed to be approximately 3.5 grams per centimeter, multiplied by the length of that little chunk, which would be from 0 to 2, about 2 centimeters. And to get the total mass, I would simply have to do assumptions and calculations like this for each of the chunks of rod that I'm given to work with. That estimate of the mass is probably going to be pretty bad. But if I took this same rod and I recorded the density at additional positions, if I recorded the density here, if I recorded the density here, maybe I recorded the density at even more positions, the more measurements I take and the shorter these little rod pieces become, the more accurate my estimate of the total mass would become. So in this situation, as I take more and more recordings, as I collect more and more data, as the little length of the pieces of rod becomes smaller and smaller, my sum becomes more accurate. And the sum, as the accuracy increases, becomes an integral. An integral. And so what I would say in the language of this class is that mass is an integral. Mass is an integral. It is a sum. A sum of what? Mass can be found by adding together density times length. So I would say that mass is an integral of density with respect to length. So that's what Calculus 2 is all about. Calculus 2 is all about integrals. Calculus 2 is all about these sums, sums that are used to calculate physical quantities, sums that become more accurate as you collect more and more data and you get more information. In this class, we're going to learn more applications of the integral, more of the physical things that it can be used to calculate. We're going to learn how to mathematically find integrals ourselves. Yeah, that's really it. How do you find the integral and then how do you use the integral is what this class is all about. Now that's Calculus 2. Let's talk a little bit about the math classes that you might see after Calculus 2 if you're going in a STEM track. So one of the math classes coming up after Calculus 2 is, of course, Calculus 3. So Calculus 3 is about derivatives and integrals, is about the material of Calculus 1 and Calculus 2. But the difference is that in Calculus 3, you're going to be working with functions that have more than one output variable. You know, in Calculus 1 and 2, we're used to dealing with this function where you plug one number into the function and you get one number out. In Calculus 3, you're introduced to this idea of a function where you plug one number in and you get multiple numbers out. An example with that would be if you plugged in, for example, a specific time, and the function gave back to you an object's horizontal position at that time, and also the function gave you the object's vertical position at that time, if it was moving in two-dimensional space. Calculus 3 is all about functions like this one, and all about how to use derivatives and integrals with functions like these, functions that have more than one output variable. Calculus 4 is similar. Calculus 4 is all about how to take derivatives and integrals and apply them to a slightly different variety of function. Calculus 3 was about functions that had more than one output quantity. Calculus 4 is all about functions that have more than one input quantity. An example of how a function like this might arise is if your function is taking in your coordinates on a two-dimensional object. I tell you where the object is located horizontally, where the object is located vertically, and you tell me, for example, maybe the temperature at that position. Maybe your object is being unevenly heated, and so I tell you the coordinates of a certain location on the object, and then the function tells me back the temperature. This would be an example of the kind of functions that you deal with in Calculus 4. So this is the subject of Calculus 4, these functions, and how to do derivatives and integrals with these functions. So to succeed in Calculus 3 and to succeed in Calculus 4, you can imagine that you need to know derivatives and integrals really, really well, because you're going to have to just use derivatives again, use integrals again, just in a slightly different setting, just with slightly different kinds of functions. And so the structure of this class is designed with that in mind. I really want you to leave this class knowing integrals really, really well, so that when you get into Calculus 3 and you get into Calculus 4, you have the skills you need to be successful. To wrap up the gist of today's video, an integral. An integral is just a sum. In particular, an integral is a sum where the amount of data that you've recorded is really large, or put another way, the gaps between the data that you have recorded are very, very small. As a result, the integral gives you a very accurate calculation of whatever physical quantity you're interested in your scenario. Calculus 2 is all about integrals. First of all, how do you calculate an integral? And second of all, how do you use integrals in various physical applications? In order to be successful in Calculus 2, in order to be able to calculate these integrals effectively, you really want to know the derivatives from Calculus 1 very well. And in order to be successful in future math classes like Calculus 3 and 4, you're going to need to know both how to find derivatives efficiently and quickly and easily, and also you're going to need to know how to find integrals effectively, quickly, and easily.